Right. So as we continue with our videos, now we are going to be looking at cyclic quadrilaterals, okay, without wasting any time. Now, remember what a quadrilateral is, right? Whenever we speak of a quadrilaterals are basically four-sided figures, right? Any four-sided figure is a quadrilateral. But now, if we speak of a cyclic quad, what do you think that is? A cyclic quad has to be a quadrilateral that lies inside, right, a circle. So if we have a circle like this, then it has the following. This one, it has a line like that, another one there has this and that. This is known as a cyclic quad. So you should make sure that the figure that you are referring to touches the circumference 4 times. As you can see, all points of the quadrilateral lie on the circumference of the circle, which means if I have something like this, this will not be a cyclic quad, right? Let's say this is O, and we have this as A, B, C, D. So the cyclic quadrilateral in this case is A, B, C, D. But if you look at A, B, O, D, it's a quad, but it's not a cyclic quadrilateral because it touches the circle circumference 1, 2, 3 times. The fourth one is at the center, so this is not cyclic. Only A, B, C, D is cyclic. So the first theorem that we look at under this is the one that says that the opposite angles of a cyclic quadrilateral are supplementary. Remember, the word supplementary simply means that they add up to 180 degrees. So add up to 180 degrees like that. So which angles are we talking about? These F when added to D, so angle F plus angle D should give us 180 degrees. They are the opposite angles. As you can see, FEDG is a cyclic quad, and also the other angles. Now this angle right there and that angle there should add up to 180 degrees. Angle G plus angle E should give us what? 180 degrees. Okay, and the reason to use for this as specified there, it's going to be opposite angles of what? Of a cyclic quad there, the accepted reason according to the examination guidelines, right? And then if you look at this one again, it's still a cyclic quadrilateral because it is a four-sided figure that touches the circle circumference how many times? 1, 2, 3, 4 times, which means the angle G when added to angle E, because they are the ones which are opposite to each other, should give us what? Should give us 180 degrees. Okay, and also what? Angle F when added to angle D should give us 180 degrees. Of course, this one we must learn the proof. Right, let us quickly go through the proof of this theorem. So remember what we said. First of all, we have that sketch, right, and then let us have our cyclic quadrilateral, which looks like, let's have something like this. Right, so this is a cyclic quad given this circle with the center of O and the points A, B, C, and D that lie on the circumference of the circle. Let's prove what we are required to prove, that the opposite angles, being angle B added to angle D, will give us 180 degrees. What are we given? Nothing of value, so I'm going to skip the given part. I will just go straight to the construction. So the construction, we are going to construct as usual, but we cannot construct through the angles that we are using to prove. So since we are proving B and D, it means no construction must go through B and D. So we will just have a construction through A and have another construction going like that. So we are basically joining OA and what? And also joining OC like that, which gives us the two angles. This is angle O1, that's angle O2, like that. So we go straight to the proof. Now this proof, you are going to use the angle at center to prove this. So as you can see now, the angle, let's take O2. Angle O2 will be none other than what? Than twice angle D. Why is that? If you look at this, you will see angle D is this is that. So the line, the arc AC subtends the angle O2 at the center, but the very same arc subtends angle D at the circumference. So angle O2 is twice angle D, right? Why is that? This is angle at center, which is equals to what? Which is equals to 2 times angle at circumference. So we are using another theorem to prove another, right? So This is also true for angle O1. The arc AC subtends that angle B, but the very same arc subtends which angle? This one. Remember that diamond thing? Similar to this now. So we have angle O1, which will be what? Twice angle B. For the very same reason, angle at center equals to 2 times angle at circumference. But if we add angle O1 to angle O2, this should give us 360 degrees. And why is that? These are angles around a point, or it's simply a revolution. But we do have angle O1 and angle O2. Angle O1 is calculated to be twice angle B, right? Sorry, 2 times angle B. Angle O2 is calculated to be twice angle D, right? Which should give us what? 360 degrees. Factor out the 2, which will give us angle B plus angle D, and this is equals to 360 degrees. Divide both sides by 2. This leaves you with angle B plus angle D, which is equals to 180 degrees, as we were trying to prove, right? If we constructed, again, if we wanted to prove for A and C, we would construct through B and D. This would give us that angle A plus angle C should also be equals to 180 degrees. Okay, now let us look at the application of this. Of course, there's the proof there. So they were proving pretty much the same thing. You go through that, but it's pretty much what we've done. So let's quickly move on. Let us look into this. First of all, we need to decide, is A, B, C, D a cyclic quadrilateral? Yes, it is, because all the points A, B, C, and D lie on the circumference of the circle, forming that four-sided figure, right? So by default, we should have what? We should have X plus 70 degrees. In fact, this starts from angle A added to angle C, which should give us 180 degrees. Reason? Opposite angles of what? Opposite angles of a cyclic quad, like that. Okay, and then we have X plus that, which is 180 degrees. By default, X will be equals to 180 minus 70, which is 110 degrees. And we can also find Y. If you look at Y, you will see that these are opposite angles of a cyclic quad. So Y plus 80 degrees again, which should give us 180 degrees. And then what? These are opposite angles of a cyclic. Right. So as you can see, we get Y, which is equals to 100 degrees. Straightforward. Okay, even if you look at this one, we should find X first before we find Y. But if you look at X, it is easier to find X if we look at the triangle. Which triangle? If we focus on triangle ABC, in triangle ABC, we can see we only have one unknown angle there, which is what? Which is angle X. So when we add 80 plus 68 plus X should give us 180 degrees. And what is this? These are angles in a triangle, sum of angles in a triangle, right? So when we do 80 plus 68, which gives us 148, right? And then 180 minus 148, it means X is equals to 32 degrees. We have that. Now we have this whole angle right here, which will be 54 plus 32, right? Which gives us 86. So this whole angle C will be equals to 86 degrees. And then, which one should we find? Let's find Y. If you look at Y, you will see that Y and that angle are opposite to each other. So angle B plus angle D should give us what? 180 degrees, and these are opposite angles of a cyclic, right? Okay, of a cyclic quad, like that. But B and D are none other than what? We have B, which is 80, so and D is Y, which is 180 degrees. So we have Y, which is equals to 100 degrees when we subtract 80 from both sides. And then we should focus on finding angle Z. But if you look at this, you will see that the angle A, when added to angle C, should give us 180 degrees, because these are the opposite angles of what? Of a cyclic, of that cyclic quad. Then from here, we do have what? A is given to be 68 plus Z. That's the whole of angle A. Plus angle C, we calculated this to be 86, which is 180 degrees. Transpose everything, then you will end up with Z, which is equals to what? Which is equals to 180 minus 86 minus 68, which should give you 26 degrees in the end. Okay, should make sense. Let us look at this. Same thing over and over again, but now we are given that O is the center of the circle. Since O is the center of the circle, remember that this line AD will then be a diameter, and a diameter subtends a 90 degrees at the circumference. So by default, we do have the angle Y. And in fact, we should start with A. Now let's count. Is this a cyclic quadrilateral? Yes, it is a cyclic quad because we have that line circumference to circumference, that chord circumference to circumference, this one, and lastly that one. So by default, if you look at x, x is opposite to d. So angle B added to angle D should give us what? 180 degrees. And these are the opposite angles of what? Of a cyclic quad. Makes sense? And then from here, opposite angles of a cyclic quad, B is x, D which is 50 degrees should give us 180 degrees, which means x should be 130 degrees like that. Okay, then we should find y, angle y, which is none other than what? Than 90 degrees. 90 degrees, why is that? These are angles in a semicircle or angles on a diameter. Okay, and then we have the last one, angle z, which is equals to 90 degrees minus 50 degrees, because we have a right angle triangle there, and these are angles in a triangle. So we are done. 90 minus 50, which is 40 degrees right there. Okay, then we look into what the next one says, that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Right, the interior opposite. I want you to think of it this way now. Right, I always think of it like as if it's a Z shape. Remember now, when we were doing geometry is fun, we used to have the Z shape, whereby what we would do is we would say that this angle is equal to that interior angle. So those two angles are equal to each other. But the cyclic quadrilateral says interior opposite, which means this angle right here, if we had parallel lines, it was going to be equals to that. But it says interior opposite. This is the interior opposite. So angle A will be equals to angle C1. And even if we can extend, maybe let's say we can produce AB, then have two angles B1 and B2 there. The angle B2, remember we skip. If it were parallel lines, this would have to be equals to that. But since it says interior opposite, you skip C2, then you choose D. So angle B1 would have to be equals to angle D. Even if we were to produce this one now, such that we have A1 and A2, we go for A1, which is the exterior, the angle outside the cyclic quadrilateral. We skip this, we take that. So angle A2 would have to be, sorry, angle A1 would have to be equals to angle C2. Makes sense. And this is under what? The exterior angle of a cyclic quad. Exterior angle of cyclic quad. And you do not have to prove this. Lucky for you. If you know how to, the previous one, you must know how to prove. This one is not a common problem. It's not a common proof. So let's look at this. In the figure, QS and PR are diameters. So we have two diameters. Usually when I see a diameter, I like to mark the 90 degrees so that I know what I'm working with. So QS is a diameter, which means this has to be a 90 degrees. It's subtended by that. And then which other diameter? Okay, we have QS. The very same QS subtends another angle there, which is this one, as you can see. But we also have PR. PR subtends this angle at the circumference. So PR subtends that 90 there. Any other 90 degrees? Okay, I don't see any. Right. So let's see. At diameters of the circle with center O. PQ is parallel to SR. Where's PQ? There it's given. This is PQ, which is parallel to SR there. What else? PS is produced to N. There's, sorry. Yeah, PS is produced to N. Where's PS? PS is produced to T. Sorry, yeah. PS is produced to D. There it goes. And then we have T is a point on the circle such that Q1 is equals to Q2. So this one is equals to that. Fine. SN is drawn. QS intersects that. Then we have the angle S1, which is 48 degrees. Calculate the size of angle Q1. So we need to find Q1 first. But if you look at this, you will see the following now. We have a cyclic quadrilateral which runs from here, goes to there, and it goes here, and we have that. Right, but that line is produced to give us the exterior angle of the cyclic, which goes like that. And in fact, this whole angle here, which is S1, should be equals to angle Q. So we have angle Q. Angle Q is equals to angle S1, and they should both be equals to 48 degrees. Why is that? This is the exterior angle of a cyclic, right, of a cyclic quad. So we do have angle Q, but remember that angle Q is made up of what? Of angle Q1 plus angle Q2, but they told us that Q1 is equals to Q2, right? Therefore, which means then Q1 has to be the half of Q. and in fact it will be half of 48, which gives us 24 degrees. Okay, like that. And then we should find angle R. Where's angle R? As you can see now, R is this one. We need to backtrace. When we backtrace, we can see that R originated from that chord, what? The chord PS. But the very same chord subtends another angle there, which is Q1. So R is equals to Q1. Angle R will be equals to angle Q1, and they should both be equals to 24 degrees. Why is that? These are angles in the same segment, right? Previous theorems. And then we have angle M1. We have to find angle M1. Where is M1? M1 is this angle right here. You should try by all means to use everything that has been given to you. They spoke about parallel lines, but I don't remember using parallel lines. So if I look at that, then you will see the following. This line right here, let me try to remove some stuff. Let's remove this. If you look at this, you will see that this blue line right here, which is this one, is parallel to what? Is parallel to that one there. And they are cut by this transversal line which goes this way. And since this is that, we can see that this angle is in a corresponding position as that. And in fact, angle M1 should be equals to what? Should be equals to angle Q. Why is that? These are corresponding angles. Since the line PQ is parallel to the line SR. And then from here, what is M1? M1 will be none other than angle Q. Remember, angle Q is what? Angle Q is 48 degrees. So those two should be 48. Okay, now moving on. We have this quite complicated scenario, but let's see how far we can go. So given this one right here, the first question is, we have the statement in the diagram. And let me give you a piece of advice. If you try to solve a problem, then you feel that it's becoming too complicated, go back, read the statement. Go back, read it for the second time, for the third time, for the fourth time, until everything makes sense, and try to underline key terms there. So let's see. In the diagram below, PQ is a common chord to of the two circles. The center M, so the center M is what? Of the larger circle lies on the circumference of the smaller circle. So at least we have a center on the bigger circle like that. Right, PMNQ is a cyclic quadrilateral. Maybe we should highlight that. P what? MNQ. So we have P. Where's M? There's M. Where's N? There's N. And then we have it's PMNQ. So this is the cyclic quad that they are speaking about. This one right here. Okay. Then let's move on. Qn is produced to R. Where's Qn? Qn was extended or produced all the way to R right there. Right, a point, R is a point on the larger circle. We have Nm produced mid-chord. Okay, let P2 equals to X. First question, give a reason why N2 is equals to X. As you can see now, N2 is outside the circle, but we spoke about it. Exterior angle, remember this line was produced, it was extended, right, such that it went all the way to R, giving us the exterior angle of a cyclic quadrilateral. If it were parallel, we take this and that, but since it's not parallel, we don't take this, we take the interior opposite. So P2 will be equals to N2. Angle P2 is equals to N2, and they are both equals to X. Why? Because that's the exterior angle of a cyclic quad. Okay, so that's how it goes. And then moving on, what do we have? We have write down another angle in size, equal in size to X. So we are looking for another angle that is equals to X. Okay, so first of all, we can see that the line PM, look at it, PM has to be equals to the line what? The line MQ, because they said M is the center of the larger circle. P and Q are points outside the larger circle, on the circumference of the larger circle. So by default, we can see that this line right here is equals to that line right there, both radiuses. So this is because they are radii. But we know one thing, that since this is equals to that, we have an isosceles triangle. And if we have an isosceles triangle, the angle P2 should be equals to the angle Q1, and J should both be equals to X. And these are angles what? Opposite equal sides. Right, by default, we have this as X. They said write down one other angle, we are done. Right, determine in terms of R, the size of R in terms of X. Where's R? R is far down there on the circumference. But if you look at R, R was subtended by the points P and Q. Right, P and Q went on to subtend R at the circumference of the bigger circle, but the very same points went on to subtend angle M1 at the center. This is twice that. So firstly, let's find angle M1. When we do angle summation, angle P2 added to angle Q1 plus angle M1 in that triangle. Let me be specific. In triangle what? In triangle PMQ. So in PMQ, we have the following. P2 plus Q1 plus M1 should give us what? 180 degrees, and these are angles in a triangle. And once we have that, P2 is X. Q1 is also X, plus M1, which is an unknown, should give us 180 degrees. This is 2X. Therefore, angle M1 will be equals to 180 degrees minus this 2X. Right, so minus 2X. That's the angle there. 180 minus 2X. But like we said, chord PQ subtends angle M1 at the center, but the very same chord subtends angle R at the circumference, which means then angle M1, which is at the center, is twice what? Is twice angle R, right, which is at the circumference. And this is angle at center, which is equals to what? Which is equals to 2 times angle at the circumference, right? And then from here, what is M1? We do have M1 to be 180 minus 2X, which is 2 angle R. Right, divide by 2, divide by 2. 180 divided by 2 is 90. 2x divided by 2, which is just x. So angle R is equals to 90 minus x. Right, moving on. Let's look at this one. Again, what do we have? In the diagram, O is the center of the circle. A, B, C, D. A, B, C, and D are points on the circumference. And if you look at A, B, C, and D, they just told us that these lie on the circumference, giving us a cyclic quadrilateral that looks like that. Okay, and then the line CD was extended like that. By default, I'm already seeing that this is the exterior angle, which is equal to the interior opposite angle. Right, chord DC is produced to E. We've already worked with that. AC is drawn. DOC is 80 degrees. Angle at center is 80 degrees. And BCE is also 80 degrees. Let's work. Calculate the size of angle DAC. Where's D? DAC. They are looking for this angle, which is what? They are looking for A1. They are just looking for A1, which is DAC. But if you look at this, you will see that the angle DOC, which is at the center, is twice angle A1 by default. It's twice DAC. It's twice the angle DAC, which is at the circumference. Right. Why is that? This is the angle at center, which is equals to what? Which is equals to 2 times angle at circumference. Alright. Like that. Do we have DOC? Yes, we do. This is 80 degrees, which is twice of what? Twice DAC. So by default, the angle DAC that they are looking for is equals to 40 degrees. Right, DAP. Where's DAP? DAP is the whole of that angle. Now, we've already found this one. Remember, we said DAP will be equals to what? The angle outside with the 80 degrees is equals to 80 degrees. And this is the exterior angle of what? Of a cyclic quad. Okay, and here, what is BAC? Where's B? BAC. They are looking for what now? They want you to find A2. Basically, you are looking for A2. So this should be easy stuff. Why is that? Because we have the whole of angle DAB, which is made up of 2 parts. It's made up of the part which is A1, but let's just call it DAC, and the other part which is what? Which is A2, but A2 is called BAC. So this is BAC. Like that. We don't even need a reason for this. DAB was calculated to be 80 degrees. DAC was calculated in number 1 to be what? To be 40 degrees plus what? Plus BAC. Right. Hence we have what? We have BAC to be equals to 40 degrees as well. Which means the line AC bisects angle A. This is equals to that. This is equals to that. Right. And that marks the end of cyclic quadrilateral. So we will be back with tangents, and then we should be done.